Hi. In this video, we are going to continue our journey through the Math Olympiad course, and we'll talk about inequalities. We have obviously done inequalities before, but that was a section on basic inequalities. This section is slightly more advanced, and we'll do more sections after this as well, where we'll go into each of these inequalities in detail and look at more tougher problems. But for now, I just wanted to share a few types of problem solving techniques concerning inequalities that you should be aware of. So we'll look at a few questions in this video, and hopefully we'll learn from them and try to uh, inculcate those problem solving techniques while we solve problems. So as usual, when I share the questions, you should try them yourself. You should pause the video and try them yourself. And if you don't get it, then you should look at the solution. That is the best way to learn. So let's start. The first question is this. Suppose there are three real numbers, A, B, C. All of them are greater than -1. A, B, C are all greater than -1, and they satisfy A cube plus B cube plus C cube equal to 1. You have to prove that A plus B plus C plus A square plus B square plus C square is less than equal to 4. Okay, so let's think about this. How do we prove this inequality? A plus B plus C plus A square plus B square plus C square is less than equal to 4. Now, one way here is to look at the target inequality and try to use this somehow here, right? So how can we use this? A cube plus B cube plus C cube is 1, and here you have 4 plus 4 right here. So I can write it like this: A plus B plus C plus A cube plus B cube plus C cube is less than equal to, instead of 4, I can write 3 plus A cube plus B cube plus C cube, right? Because 3 plus 1 is 4. And this can be written as 1 plus A cube plus 1 plus B cube plus 1 plus C cube, right? So basically what I've done is I've converted this 4 into something symmetrical in terms of A, B, and C. This is the same thing as 4, but it is much better now, because now we can understand the inequality that we need to prove. A plus, this is A square, B square, C square actually here, left hand side. A plus A square plus B plus B square plus C plus C square. I have to show that it is less than equal to 1 plus A cube plus 1 plus B cube plus 1 plus C cube, right? This is the same inequality, but it is a much easier inequality to prove than the starting point here. Now, you should realize that if you can prove that A plus A square is less than equal to 1 plus A cube, and B plus B square is less than equal to 1 plus B cube, and C plus C square is less than equal to 1 plus C cube, then you are done, because you can add the three inequalities and get the answer. But this is quite easy actually. You can consider the function f of x is equal to 1 plus x cube minus x square minus x. And this function, you will be able to factorize this function and take 1 plus x common, and it will become 1 minus x whole square. You should try factorizing this function. This function is greater than equal to 0 for all x greater than -1, right? If the function can be factorized as this part is positive and this part is positive if x is greater than -1. So we know that this function is positive for x greater than equal to -1. So obviously then f of A, f of B, f of C are all positive, because A, B, C are all greater than -1. And then you are able to prove these three inequalities, and adding these three, you get the desired inequality in the problem. So I'm not outlining all the steps. I want you to work through the remaining details yourself. But it is pretty obvious. You have to choose a function here which helps you prove these intermediate inequalities, which upon adding, you will get the overall desired result. Let's move on to the next question. In this question, we have let ABC be the sides of a triangle, and let m be greater than 0. Prove that a by a plus m plus b by b plus m is greater than c by c plus m. We have to show that this quantity is true. Now, again, we can do this by simple analytical method where we just simplify what we need, right? So I'll show you what is the analytical method here. We just simplify it properly. So we say a times b plus m plus b times a plus m by a plus m, b plus m is greater than c by c plus m. I need to show this, and if I can show this, that would imply the original inequality, right? Because I'm just taking LCM here and adding. Notice I've written this implication, and this implication is like a backward implies. Like if this is true, then it implies this, right? So if I can construct a series of such backward implications, finally, if I get something true, like for example, if I get 1 is greater than 0, that implies this, and that implies this, and so on, then if this last statement is true, then I have proved the original inequality, right? Obviously, that will not happen actually. Like we'll not get something as obvious as 1 is greater than 0. But the idea is this. I'm going to simplify this here. I'm going to simplify this here, and I'm going to try to get it to an obvious inequality. Okay, and I will always write backward inequalities at backward implications at each step, right? So this becomes 2ab plus m into a plus b by m square plus m into a plus b plus ab is greater than c by c plus m. Basically, I'm simplifying this only, and I'm saying that if this was true, then this is true, and if this is true, then this is true, right? So I have this, and if I take a reciprocal at this stage, m square plus m a plus b plus ab by 2ab plus m a plus b is less than m plus c by c. I have to reverse the inequality if I take reciprocals. And then from here, I can write this as 1 plus m square minus ab by 2ab plus mab is less than 1 plus m by c. And 1 gets cancelled now. And finally, here I will get m square c minus a minus b is less than ab 2m plus c. Basically, finally, after simplifying all of this, I am getting this, right? Now think about it. We are saying that A, B, C are sides of a triangle. So by triangle inequality, A plus B is greater than C, right? And if A plus B is greater than C, then C minus A minus B is less than 0. C minus A minus B is less than 0. M square is greater than 0. So this left-hand side is less than 0. Whereas this quantity here is greater than 0 because all of the terms here are positive, right? A, B, and M are positive. So what we have gotten here is a obviously true inequality. Something less than 0 is less than something positive, right? So if you now reverse all the steps, from here we can show that this is true, from here we can show that this is true, from here we can show that this is true. We are able to reverse all the steps and prove the original inequality, right? So it's a series of analytical manipulations and transformations, and eventually you are able to get the original inequality that was desired, right? Okay. Let's look at the next problem. Okay. In this one, we have A is greater than B is greater than 0. We have to prove that root 2a cube plus 3 by ab minus b square is greater than equal to 10. Okay. It looks weird, but it's actually a straightforward question. We have AB minus B square is equal to A minus B into B, which is greater than 0. Why is greater than 0? We have A minus B is positive and B is also positive, right? Now, because these are two positive numbers, I can do AMGM and I can say 0 is less than A minus B into B is less than equal to A minus B plus B by 4 and this whole square, right? This is basically saying that xy is less than equal to x plus y whole square by 4, which is a true statement. It's an AMGM inequality. We just squared the AMGM inequality, right? So this basically is equal to A square by 4, right? Therefore, root 2 times A cube plus 3 by AB minus B square is greater than equal to root 2 times A cube plus 3 by A square by 4. Because if you divide by a greater quantity, the value will be lesser, right? So this must be greater than equal to this, which is equal to basically root 2 A cube plus 12 by A square. Now I want to do AMGM to find the maxima minima of this quantity, and I want to do AMGM in such a way that I get a numbered value or a value that something like this, right? I need to prove it's greater than equal to 10, right? So how do I do AMGM on this stuff to get a minimum value? I need to be able to cancel the powers of A somehow, right? So one way to do that is to not do AMGM directly on these two terms, because then A's will not cancel, right? But we can do AMGM on a combination of the terms. So if I divide this term into two halves, root 2 by 2 A cube plus root 2 by 2 A cube. Basically, when I do AMGM, there will be A power 6. And then I can divide this term into three halves. So 4 by A square plus 4 by A square plus 4 by A square. What is the benefit? Then in the denominator also, I will get A power 6 when I do AMGM and the product. So this must be greater than equal to 5 times fifth root of root 2 by 2, root 2 by 2, 4, 4, 4, and A power 6 by A power 6, right? So this gets cancelled and you have basically 1 by 2, and this is 64. So 64 by 2 is 32. So 5 times fifth root of 32 is 10, right? So this is greater than equal to 10 is coming obviously by AMGM. Understand the technique. How did I get the numerical 10 value? Because I split the terms into such number of parts that I was able to cancel the A powers when I did GM product, right? So A cube I divided into two terms so that I get A power 6 on top, and A power square below 1 by A square I split into three terms so that I can cancel the A power 6 from the A cube, right? So that is a common technique, that is a standard technique, and we can show basically that this is greater than equal to 10. You should learn this technique. You will need it in your future problems later, right? This next question here, I will not do the full solution. I will just outline how you should go about the solution, and I will leave that to you. We have suppose A, B, C is greater than 0, and we have A plus B plus C is greater than equal to ABC, right? Prove that among the three inequalities, what are the three inequalities? 6 by A plus 3 by B plus 2 by C is greater than 2, greater than equal to 2. 6 by A plus 3 by C plus 2 by 6 by B plus 3 by C plus 2 by A is greater than equal to 2. And finally 6 by C plus 3 by A plus 2 by B is greater than equal to 2. Prove that among the three inequalities, at least two are valid. We need to show that at least two are valid. So basically that means that you need to show that either all three are valid or two of them are valid, exactly, right? However, directly proving it will be difficult. To prove that two of them are valid, you will have to take so many cases, right? So what we will try here is a proof by contradiction. Proof by contradiction. And if you think about it, what is the statement that we are contradicting? We are contradicting the statement that at least two are valid out of these three, right? So we can say the contradictory statement should be none of them are valid. Case one is none of them are valid. And case two is only exactly one of them is valid. Exactly one of them is valid, right? So the contradiction has two cases basically. None of them are valid and exactly one of them is valid. Now for the exactly one of them is valid, you can assume whichever one is valid and the other two are invalid. So that is up to you. You can do it without loss of generality. You can assume one of them is valid. I will show you the contradiction that comes when none of them are valid. You should try and do the second part of it yourself, right? So case one, I will show you the contradiction. So if none of them is valid, you have the inequality 6 by a plus 3 by b plus 2 by c is less than 2. And you have 6 by b plus 3 by c plus 2 by a is less than 2. And you have 6 by c plus 3 by a plus 2 by b is less than 2. If you add all these three inequalities, why are we saying less than 2? Because we know none of them are valid. None of these are valid. So it has to be less than, not greater than equal to. If you add these inequalities, you get 11 times 1 by a plus 1 by b plus 1 by c is less than 6. So which implies that 1 by a plus 1 by b plus 1 by c is less than 6 by 11, right? We are getting this as a conclusion from our assumption in this case, right? Because we assume none of them are valid, we are getting this result, right? However, we can also say, if you want to analyze 1 by a plus 1 by b plus 1 by c whole square, think about it. We can say that 1 by a plus 1 by b plus 1 by c whole square will always be greater than 3 times 1 by ab plus 1 by bc plus 1 by ca. Why is that so? Because when you do the square here, you'll get 1 by a square plus 1 by b square plus 1 by c square plus 2 times 1 by ab plus 1 by bc plus 1 by ca. And greater than equal to 3 times this basically means that you are saying this implies that you are saying 1 by a square plus 1 by b square plus 1 by c square minus 1 by ab minus 1 by bc minus 1 by ca is greater than equal to 0. Now this is correct. This is correct because we have a inequality like this, standard inequality, right? A square plus b square plus c square minus ab minus bc minus ca is greater than equal to 0. Because it can be shown that this is half of a minus b whole square plus b minus c whole square plus c minus a whole square, right? Because this is half of this, similarly we can show that this is also true because it is half of 1 by a minus 1 by b whole square plus 1 by b minus 1 by c whole square plus 1 by c minus 1 by a whole square. So that has to be positive. So this is true, then that implies this is true. And if this is true, we have this is true, right? Now I will establish a contradiction now because I know 1 by a plus 1 by b plus 1 by c whole square is greater than this. And if you simplify this, this becomes 3 times a plus b plus c by abc, right? If you add these terms, you will get a plus b plus c by abc. But the problem itself says that a plus b plus c is greater than equal to abc. So that means that this is greater than equal to 3, right? So we are getting from here, we are getting 1 by a plus 1 by b plus 1 by c whole square is greater than equal to 3, which means 1 by a plus 1 by b plus 1 by c is greater than equal to root 3, right? And we already saw that 1 by a plus 1 by b plus 1 by c should be less than 6 by 11. These two are contradictions, obviously. So basically, we have shown that the case that none of the inequalities are valid leads us to a contradiction, because we always have 1 by a plus 1 by b plus 1 by c is greater than equal to root 3 under the condition that a plus b plus c is greater than equal to abc, right? So I've established a contradiction in this one case. The one case that I have left for you to try yourself is the case where exactly one of the inequalities is valid. So you should try that yourself. We'll now look at the last problem for this video. This is, suppose xyz belong to real positive and x plus y plus z is equal to 1. We have to prove that 1 by 1 plus x square plus 1 by 1 plus y square plus 1 by 1 plus z square is less than equal to 27 by 10. First of all, we know that x, y, z are real positive. So x, y, and z are between 0 and 1 because they satisfy this also. Also, you can check that if x plus y plus z is 1 and each of x and y and z is 1 by 3, you are able to satisfy this inequality. The equality happens in that case when 1 by 3 is put, right? You can check that. Now, in order to get this inequality, I'll make a claim and then I will see whether my claim is true or not. So I will say that let's assume that there exist constants a and b such that 1 by 1 plus x square is less than equal to ax plus capital B, right? For x belonging to 0 to 1. So 1 by 1 plus x square, I'm saying, is less than some linear function, right? And when x belongs to 0 to 1, right? So if that is true, then similarly 1 by 1 plus y square will be less than equal to ay plus b and az plus b and all. And we can say that the equality, these two are equal, happens that x is equal to y is equal to z is equal to 1 by 3, right? So the equation 1 by 1 plus x square is equal to ax plus b has multiple roots. Multiple roots because it happens for x also, y also, z also. Multiple roots at x is equal to 1 by 3, right? So this equation, basically you can rewrite now. We can say 1 is equal to 1 plus x square into ax plus b. And this polynomial, basically we can say that this polynomial should be similar to x minus 1 by 3 whole square and small ax plus b, right? Because this polynomial has multiple roots at x is equal to 1 by 3. Right? You can basically try and compare coefficient, or you don't even need to write it like this. You can just say that this equation has roots at x is equal to 1 by 3, multiple roots, right? So just simplify this and say that x minus 1 by 3 is a factor, right? And compare coefficients, and you should get the idea that the term looks somewhat like x minus 1 by 3 is a double factor, so it should be x minus 1 by 3 whole square, and remaining term will come out to be x minus 4 by 3. So basically from here, from the fact that 1 plus x square is equal to ax plus b has multiple roots, we are getting the nature of the function that we need to focus on here. This is x minus 1 by 3 whole square multiplied by x minus 4 by 3. So let's see what that function tells us. So if you have this function 3x minus 1 whole square x minus 4 by 3, let's look at this function. Notice that I have just taken the 3 inside because it was x minus 1 by 3 whole square and x minus 4 by 3. This was my function that was coming, right? I'm just taking the 3 in and the numerator, right? This function is less than equal to 0 for x belonging to 0 to 1. Why? Because this part is positive and this part is negative. Now, if you simplify this a little bit, you will be able to write it as 9x cubed minus 18x squared plus 9x minus 4 by 3 is less than equal to 0. And simplify it a little further, you'll get x cubed minus 2x squared plus x minus 4 by 27 is less than equal to 0. And you can even factorize it a little bit. You will be able to say x squared x minus 2 plus x minus 2 plus 50 by 27 less than equal to 0, which becomes x squared plus 1 x minus 2 is greater than equal to, or actually less than equal to minus 50 by 27. So you have x squared plus 1, 2 minus x multiplying by minus 1 is greater than equal to 50 by 27. And from here we get 1 by 1 plus x squared, 2 minus x is less than equal to 27 by 50. So what we are getting eventually from this function is that 1 by 1 plus x squared is less than equal to 27 by 50 into 2 minus x, right? So we have established our original function. Think about it. We started by saying that 1 by 1 plus x squared is less than equal to ax plus b, right? And if I can show that, then I will be able to show the proof, right? Because I have gotten now 1 by 1 plus x squared is less than equal to 27 by 50 into 2 minus x. Similarly, 1 by 1 plus y squared will be less than equal to 27 by 50 into 2 minus y. So if I add the three versions here, I will get the required inequality sum is less than equal to 27 by 50 into 6 minus x minus y minus z, and x plus y plus z is equal to 1. So this is 5. So it will be 27 by 10. So sum is less than equal to 27 by 10 will appear, right? How did I get this? How did I get this function first of all? I got this function by realizing that this inequality is going to be an equality at x is equal to 1 by 3. So that means x is equal to 1 by 3 is a double root of the polynomial, cubic polynomial that comes here. You have to simplify this polynomial, get a cubic polynomial, and say that x minus 1 by 3 whole square is a root. So after that, it's just about comparing coefficients and factorizing to get what that polynomial or ffx should look like. And this is what it should look like. And then we focused our attention on this polynomial and proved that 1 by 1 plus x square is less than equal to this. So it is a little tricky, but the idea was based on the claim that I want to show that 1 by 1 plus x square is less than some linear function. And I can see that x is equal to 1 by 3 satisfies the equality condition, right? So that's it for this video. You should try and fill in the blanks wherever you have not understood something or you need a little more clarity. Try the questions yourself. Let me know if there is any difficulty. Obviously, this is not the end for our inequalities discussion. There are many more videos on inequalities coming in the future. But for now, I just wanted to show you some of these techniques and get you familiar with them. And I'll see you next time in the next video.